welcome to the Complete History of Science. Series 7, Episode 8, The Harmony of Johannes Kepler. In 17th century Europe, news could spread surprisingly quickly. Important men, such as courtiers and diplomats, exchanged information through a network of letters that spanned the continent. Typically, those involved needed to keep tabs on political developments, but they also frequently took a wider interest in scholarly and artistic work. Letters discussing the most recent scientific developments were highly valued and often copied, forwarded, and sometimes published, expediting the flow of new knowledge. One of the central hubs of this great network was the court of the Holy Roman Emperor in Prague. Wacke von Wachenfels, a diplomat at the court and a man with broad intellectual interests, maintained correspondence with many learned men. Through his contacts in Italy, Wacke heard whispers of Galileo's new discoveries with the telescope and brought them to the attention of his good friend, the imperial mathematician Johannes Kepler. The initial rumour which Wacke received said that Galileo had discovered 4 new planets. This would have been a remarkable event in the 17th century. No new planets had ever been discovered. Mercury, Venus, Mars, Saturn and Jupiter had been known since time immemorial. The two men excitedly discussed the report, but Kepler also felt some ambivalence. He was still clinging to his polyhedral theory, which he believed explained that there were only 6 planets. Wacke suggested to Kepler an alternative possibility. Perhaps the planets were real, but maybe instead of orbiting the Earth, they were orbiting one of the fixed stars. This idea originated from the itinerant preacher Giordano Bruno. A few years before, Bruno had wandered Italy, France and England, preaching that the universe was infinite and that the stars were like our own sun. He had also speculated that this meant the planets revolved around them. Kepler was still uneasy with the possibility. While he had relegated the Earth to a planet, he had elevated the sun to a special place at the centre of the universe. An infinity of stars would undermine this idea. To resolve his concerns, he needed to find out what Galileo had actually said. In March 1610, Galileo published his discoveries in a book called The Starry Messenger. A copy was sent by Galileo as a gift to the Emperor Rudolf, who lent it to Kepler. Poring over the pages, he was relieved to find that the 4 new planets were in fact moons of Jupiter. Rather than undermining his work, moons were useful for Kepler's theories. They demonstrated that not everything in the cosmos revolved around the Earth. Reading on, he found that Galileo had made other groundbreaking discoveries. Pointing his telescope at the moon, he had observed that the surface was rough. This undermined Aristotle's belief that celestial objects were flawless. To the contrary, Galileo reported mountains, valleys, and large craters which appeared like seas. Reading Starry Messenger, Kepler was surprised but enthusiastic. Elsewhere, the initial reception was mixed. To many, its discoveries seemed too fanciful, too unlikely. It didn't help that Galileo was deeply unpopular, particularly in his native Italy. Whilst professor at Padua, Galileo had regularly clashed with the Aristotelians, who still dominated the universities. Galileo was aware that Starry Messenger would receive backlash and sought support. A new copy of the book, personally delivered by the Tuscan ambassador, was sent to Kepler and included a note asking for his opinion. Kepler's importance owed to his position as the imperial mathematician and the heir of Tycho Brahe. Galileo also suspected he would be sympathetic. Kepler was the most prominent heliocentrist in Europe. Nevertheless, the request for support required a certain degree of audacity. Years earlier, Kepler had made a similar plea to Galileo for a comment on his new astronomy, but he'd received only silence. 15 years before that, Galileo had privately admitted to Kepler that he was a Copernican. Kepler had urged Galileo to join him publicly in supporting heliocentrism, but again, Galileo failed to respond. Kepler was disappointed by Galileo's silence, but didn't hold a grudge. He was too excited not to share his opinion. Kepler wrote a response in the form of a letter, published with the title Conversations with the Starry Messenger. It was wholly positive, and Kepler openly applauded Galileo. Scientifically, the letter is interesting as well, because Kepler places Galileo's discoveries in the context of his own heliocentric ideas. For example, Kepler discussed the observation that stars viewed with the telescope remain point-like. He noted this as a mark in favour of the Copernican system. To explain, one of the oldest arguments for a stationary Earth was that if it was moving, there should be an observable parallax in the position of the stars. This parallax had never been observed, which implied that the Earth was still. There was, however, another possibility. If the stars were very far away, maybe the parallax was simply too small to measure. Kepler said that, as the stars remained point-like when viewed with the telescope, this implied they were far away, allowing the possibility that the Earth was in motion. After the letter's publication, Galileo was slow to respond, but he did eventually express gratitude. "I thank you," Galileo wrote, "because you were the first and practically only one to have complete faith in my assertions." The battle with Starry Messenger's detractors, though, was far from over. One of the main points of doubt was the telescope itself. At the time, these devices were still new, having only been invented a few years before. Very few people owned any sort of telescope, and Galileo's were uniquely powerful, meaning no one else could verify his observations. Critics suggested that Galileo's discoveries were artifacts of the instrument. Nevertheless, Kepler defended use of the telescope. He'd seen inferior models in Prague, which, combined with his extensive knowledge of optics, was enough to convince him that Galileo's discoveries were real. Later, in August 1611, he would get the chance to see for himself. Galileo had sent a telescope to the Duke of Bavaria, who kindly lent the device to Kepler. One night, Kepler and several friends made observations of the night sky. To make sure they weren't biased, each man took turns to look through the telescope and secretly draw what he saw with chalk. Spying Jupiter, they were certain of 3 bodies near the planet, with a 4th faintly visible. Viewed across several nights, the positions of these bodies changed, but they were clearly following Jupiter, implying they were moons, just as Galileo had deduced. After confirming Jupiter had satellites, Kepler turned his attention to Mars, prompted by a strange message from Galileo. Following his public support of Galileo, Kepler had received a note of thanks, which included a curious addition, a short cipher. The message was supposed to read, "I have observed the highest planet, triple-bodied." Galileo thought he had seen moons around Saturn. But there was no key to decrypt the message. Kepler had to spend weeks trying to decode it through trial and error. He eventually settled on the solution: "Hail satellites, children of Mars." This led him to believe there were moons around Mars rather than Saturn. When he finally managed to see Mars, he was excited to note several points of light. But Viewing these points over several nights, it became clear they weren't following Mars. He concluded that they were fixed stars and not moons. Next, Kepler made observations of the moon to verify Galileo's claims. Viewed through the telescope, the irregularities of the moon's surface were clear. He could see mountains, valleys, and a large crater, which he said was shaped like the Caspian Sea. Around the end of September, Kepler returned the telescope and quickly wrote up his findings in a short work called A Narrative on the Satellites of Jupiter. This was Kepler's second publication in support of Galileo, but he hadn't finished yet. Kepler understood that observations alone would not settle the matter. One of the issues with the telescope was that Galileo couldn't fully explain how it worked. Without a theoretical basis for magnification, images seen through the device would always be treated with suspicion. If the telescope was going to be accepted as an astronomical instrument, it had to be made intelligible. Kepler prepared a new work, starting from first principles, to explain how it functioned. To do this, he had to overcome limits of earlier optical knowledge. Since ancient times, it was understood that glass could be used to bend light. But as the quality of glass was relatively low, its ability to magnify was largely unstudied. This began to change in the Middle Ages. Roger Bacon described the use of a sphere of glass to view objects at what he called incredible distances. He also wrote about how thick sections of glass could be overlaid on text to make letters easier to read. By the 15th century, lenses were being set in frames to correct for poor eyesight. Though they worked in practice, the optical principles behind lenses remained poorly understood. At some point in the 16th century, it was discovered that a pair of lenses could create a more powerful effect than a single lens. In 1558, Giambattista della Porta wrote a book called Magia Naturalis about various natural phenomena. In the section on refraction, he wrote, "By means of a concave glass, you will see distant objects, small but clear. With a convex glass, you will see near objects, magnified but dim. If you know how to combine them exactly, you will see both distant and near objects, larger than they would otherwise appear, and very distinct." Still, it took until the early 17th century for this idea to be employed in the first telescopes. Credit is usually given to Hans Lippershey, a Dutch lensmaker. Lippershey was a craftsman, not a scientist, and his device was marketed as a military tool. When Lippershey was declined a patent, other glassmakers began to make their own versions, and the tool soon spread. By 1609, word of the telescope had reached Galileo, who immediately created his own version. He followed the same design as the original, using a convex lens to focus the light and a concave lens as an eyepiece. Galileo's skill as a craftsman allowed him to grind much better lenses, meaning his devices were far superior to the competition. The convex-concave system would become known as the Galilean telescope. Kepler, in contrast to Galileo, was no craftsman and couldn't hope to create his own device. He did, though, have a far superior grasp of theoretical optics and a clear idea of how the two-lens telescope worked. In 1611, he published a text on lens optics called Dioptrice. Like much of Kepler's work, the book was mathematically dense, separated into 141 theorems, most linked to geometric proofs. In the book, he demonstrated many fundamental properties of ray optics as they relate to lenses. Kepler's understanding of refraction was limited, but by assuming that the angle of refraction was proportional to the angle of incidence, he could make progress. He demonstrated geometrically how convex and concave lenses direct light and how a pair of these lenses can magnify distant objects. Kepler's demonstrations put Galileo's observations on a firmer footing and opened the possibility that the telescope might be improved. In Galileo's design, the image produced was both upright and very well illuminated. This was crucial for early models intended for military applications. But in the case of astronomy, the orientation of the image wasn't so important, and there were clear weaknesses with this configuration. The main drawback of the Galilean telescope was that it had a restricted field of view, which limited the potential for magnification. In addition, the design was prone to optical defects, known as aberrations, the most important of which was spherical aberration. This occurs when light entering the edge of the lens doesn't focus at the same point as light from the centre. This made images from Galilean telescopes look blurry around the edges and further reduced the field of view. To overcome these limitations, Kepler described a new design. The change was simple. He replaced the concave eyepiece with a convex lens. This greatly improved the field of view and reduced the blurring effect. Interestingly, though he described it in theory, Kepler never built his telescope. It wasn't until the 1630s that the first Keplerian telescopes began to appear, and as he predicted, they had huge advantages. The design allowed much greater magnification, and hence more precise measurements. Over the next half-century, Keplerian telescopes became the dominant model. Kepler published Dioptrice in 1611 in Prague. It would be the last important work he completed in the city, as that same year his life underwent great upheavals. At the end of 1610, Barbara and 3 of his children became sick with fever. 2 of his children survived, but the 3rd, Friedrich, died. Barbara recovered too, but she became mad with grief and fell into a deep depression. Worse still, while his son was on his deathbed, the situation in Prague was becoming dangerous. The Emperor Rudolf was deeply unpopular amongst the nobility. Years of neglectful rule had allowed religious division to spread across the empire. Rudolf's family, realizing the problem, attempted to replace him with his younger brother Matthias, King of Hungary and Croatia. In a panic, Rudolf tried to shore up his authority by inviting German mercenaries into the kingdom, a decision that backfired immediately. As they reached Prague, groups of Protestants banded together to resist their advance. Chaos erupted in the city. Violence, looting, and disease spread. Rudolf had to pay off the mercenaries to get them to leave. With the crisis outside ongoing, days in Prague Castle became increasingly anxious and melancholy. The emperor came to rely on Kepler as an advisor. Primarily, he wanted horoscopes, though Kepler was reluctant to give them. Kepler had become cynical about the predictive power of astrology and didn't want to create false hope. In order to deflect some of the pressure from the emperor, however, he did publish one horoscope, predicting him a long life. This, unfortunately, was not to be, and Rudolf died in early 1612. Kepler's loyalty to the emperor was not held against him, and his appointment as imperial mathematician was renewed. But, with his patron dead, Kepler decided now would be a good time to leave. Barbara was still deeply depressed, and Kepler hoped that a change of scenery might help her recover. He looked first for a job in Württemberg, imagining that he might join the aging Michael Maestlin as chair of astronomy. The advantage of Württemberg was that it was firmly in Protestant territory, but he was rejected due to his reputation for nonconformism. In this period of religious sectarianism, there was no place for men like Kepler who sought reconciliation between the faiths. For a while, he toyed with the idea of moving to Padua to occupy the mathematics chair which Galileo had just vacated. Galileo even made a statement publicly supporting Kepler's application. Italy, though, would be a difficult transition for his family, so he decided against. Ultimately, he accepted a position as provincial mathematician in Linz, Upper Austria. This was similar to the role he held in Graz, though now he'd be allowed to keep his title of imperial mathematician. The appointment was good news, but also obliged him to complete the new astronomical tables promised to Rudolf. With full access to all of Tycho's data, he now had no excuses. Just as Kepler was making arrangements, his wife Barbara fell ill and died. Theirs had not been a happy marriage, but he still felt her loss deeply. He had chosen Linz, in part, as he hoped she would feel comfortable there. Still, with no alternative, he moved to Linz with his 2 surviving children and his stepdaughter Regina. Immediately on arrival, Kepler faced further challenges. Compared to Prague, Linz was provincial, and he was isolated from the intellectual circles he had previously enjoyed. His personal religious leanings also caused problems. The local parson recognized Kepler and knew of his views. He challenged Kepler on a point of theology, which led to an argument. In response, the parson excluded Kepler from communion at the local parish. On reflection, Kepler again mourned the fighting between religious factions, which in his words, had torn the truth to pieces. He was also supposed to be continuing work on the astronomical tables, but was having a challenging time concentrating. Despite full access to Tycho's data, progress had been slow. The tables would take an immense amount of careful calculations, and Kepler lacked the motivation. He instead found new problems to distract himself. Linz was situated on the banks of the river Danube. Kepler noticed that winemakers stacked casks of various sizes and shapes. This made him wonder, how could the volume of the barrels be calculated? If wine barrels were cylindrical, the answer would be obvious. It would simply be the area of a circle multiplied by the height of the barrel. But of course, wine barrels aren't cylindrical, they bulge in the middle. Kepler worked out the volume could be estimated if one considered the barrel to be made of thin discs of varying diameter. Adding together the volume of all of these discs would give the total volume. What's more, Kepler realized that the thinner you made the slices, the more accurate the estimate for the volume would be. To his contemporaries, this may have seemed a trivial problem, but the work would anticipate one of the most important mathematical tools developed in the century, calculus. Kepler wrote up his findings and tried to get them published in a new book, but he realized that in Linz, options were limited. So, to overcome this, he brought his own printer, a man named Johannes Planck. Kepler set up a printing press in his own home and employed Planck to operate it. To pay for this, Kepler began producing calendars. These calendars contained the usual information on saints' days and Christian feasts, as well as astronomical information such as the sun's passage through the zodiac and the phases of the moon. Their purpose was to allow buyers to make astrological judgments about the coming year. Kepler did not enjoy producing the calendars, saying that it was only a little more honourable than begging. But the capital they provided would allow the printing of his new work. Kepler began to settle in Linz. In 1613, he married a much younger woman, Susanna Reutinger, the daughter of a cabinet maker. She had been chosen from a list of potential candidates, which Kepler narrowed down like a mathematical problem. The effort paid off, and his second marriage was much happier than the first. In a better state of mind, Kepler began working on 2 new books of astronomy, The first was a textbook targeted at a general audience. He recognised that the new astronomy was incomprehensible to most readers. The mathematics was too dense, and only a handful of technical astronomers could follow Kepler's arguments. Even the great Galileo had failed to read it. The aim of the new text was to fix that. It could elaborate on his theories, such as his first and second law, and hopefully strengthen support for heliocentrism. Generously, he titled the book The Epitome of Copernican Astronomy, though in truth there was little of Copernicus there. The details were all Kepler. The first volume of the manuscript was handed over to Planck in 1616 and was significant as the first textbook to teach that the Sun was the centre of the universe. Throughout the 1610s, Kepler would continue to suffer personal setbacks. His first two children by his second wife Susanna died in infancy. Grief again consumed his household, and Kepler, as he had so often done in his life, sought solace in his work. A decade before, he read a manuscript by Ptolemy titled Harmonics, and noticed a striking similarity between Ptolemy's ideas and his own. Ptolemy was interested in why certain ratios of musical notes produced pleasing harmonies, and he'd speculated they might reflect some underlying pattern. Kepler had long been curious about the same phenomena, believing that the apparently vast and chaotic universe was based on simple rules. This was a spiritual matter for Kepler, who thought that to understand the universe was to understand God. He began with the harmonic ratios found in music. When a string is plucked once and then held down midway, a pleasing interval is sounded, equivalent to the difference of an octave. The ratio of strings in this example is 1 to 2. The ancients had noticed that only certain ratios, like 2 to 3, 3 to 4, or 3 to 5, created harmonious tones. Kepler looked for a reason for this and found one in geometry. He explained that the numbers relate to the sides of geometric figures. Some figures, such as the triangle, the square, or the pentagon, can be constructed using only a ruler and compass. Kepler said that these figures were knowable, and hence they appeared as harmonic ratios. By contrast, some figures with, say, 7 or 11 sides are not constructible. He called these unknowable and reckoned that God therefore wouldn't have used them in building the universe. This type of speculation gave Kepler tremendous joy. He felt that such knowledge brought him closer to God. Expanding on ideas for music theory, Kepler looked for the appearance of these ratios in astronomy. He knew that the planets orbited in ellipses, meaning their distance from the Sun changes. The variation seemed arbitrary, but Kepler anticipated there might be some underlying reason. He calculated the ratio of the distances of closest approach and when the planet was furthest away, hoping to see some pattern. Unfortunately, he couldn't find any, which left him very disappointed. Another search, however, was more fruitful. One of the major triumphs of Copernicanism was that when the Sun was placed at the centre, the planets fell into a natural order. The closer a planet was to the Sun, the shorter its period and the faster it travelled. Kepler began to look for harmony in the relationship between the orbital period and the distance from the Sun. Thanks to Tycho Brahe, these periods and distances were known much more precisely than in the time of Copernicus, and so Kepler could make his own assault on the problem. The work was a slow process of trial and error. He could see that the period wasn't simply varying in proportion to the distance, and so tried playing around with powers. It seemed like the period might be proportional to the distance squared. When this didn't work, he began to fine-tune until he settled on an answer. The square of the period was proportional to the distance cubed. Not a simple relationship perhaps, but certainly one which appealed to his sense of divine harmony. This would become known as Kepler's third law of planetary astronomy. The final text, which he called The Harmony of the World, was finished in May 1618. It was dedicated to James I of England, who Kepler hoped would act as a peacemaker amongst the religious conflicts erupting in Germany. It was not to be. 1618 marked the beginning of the 30 Years' War, one of the most destructive wars in European history. By the end of the conflict, as many as 8 million people died, the majority from famine and disease. The conflict had been building for some time. The Holy Roman Empire was a patchwork of Catholic and Protestant states. Many were functionally independent, but as tensions rose, they formed self-defense pacts. When Ferdinand II was announced as the new Holy Roman Emperor, his reputation as a zealous supporter of the Catholic cause led to a Protestant uprising in Bohemia. Fighting erupted, and soon countries across Europe were drawn into the conflict, on the side of their co-religionists. In 1620, Catholic troops invaded Upper Austria and captured Linz. Kepler had ties to the imperial crown, but still worried about his future. He had previously experienced Ferdinand's counter-reformation in Graz, where he had been expelled. But, for the first time in his life, Kepler's reputation for non-conformity came to his rescue. It was well known that he had been excluded by the Protestant Church in Linz, and so he was viewed as a non-partisan. When Protestants were banished from Linz, Kepler was exempted, along with his printer Planck. After his ascent to the throne, Ferdinand was even happy to reappoint Kepler as imperial mathematician. With his position secure, pressure mounted on Kepler to publish his astronomical tables. Promised to the Emperor Rudolf more than 20 years earlier, progress had been slow. The renewed urgency came not from the imperial court, but from his fellow astronomers. Astronomical tables, unlike calendars or ephemerides, are not simply a list of the positions of the planets and stars on a particular day. Instead, they allow the positions of celestial objects to be calculated at any time, potentially thousands of years into the future. His friends and peers had become restless, waiting for Kepler to complete the task. Longtime correspondent David Fabricius said self-deprecatingly that even he would have been able to complete the tables by now. At least in part, Kepler's delay was due to lack of motivation. He had greatly enjoyed working on the harmony, and in comparison, he felt dread thinking about the lengthy computations needed to complete the tables. He responded to Fabricius, "Don't sentence me to the treadmill of mathematical calculation." However, a mathematical discovery made in Scotland would have a great impact on Kepler's attitude. In 1614, John Napier published his table of logarithms. Kepler realized that logarithms would greatly simplify his calculations. In lay terms, Napier's tables reduced complex operations such as multiplication or division into the simpler operations of addition or subtraction. Despite their obvious utility, there was a great mystery surrounding Napier's tables. He had published them without explaining how they had been derived. Some astronomers, such as Michael Maestlin, were cynical. Maestlin warned against applying the tables to astronomy without fully understanding them. Kepler took heed of the warning, and instead of applying the tables blindly, he derived a book of logarithms specially adapted for his own purposes. Logarithms became a key tool in the development of the new astronomical tables. They eased Kepler's work, and by 1624 he had finally completed them, though it would take 3 years to get them published. As usual, money was an issue. Kepler travelled to Vienna to ask the imperial treasury for the funds to print the tables. Naturally, the money was not forthcoming. War had emptied the treasury, so Kepler would need to pay out of his own pocket. He looked to do the printing in Ulm, which was untouched by conflict and the home to many specialized presses. But Emperor Ferdinand, suddenly taking an interest, insisted that the tables should be printed in Austria. Kepler was forced to return to Linz and use his own printer Planck. The manuscript, with over 100 pages of numerical data, was a great printing challenge, made more difficult when fighting once again broke out near the city. Kepler's home on the city wall had to be garrisoned by soldiers when a peasant army laid siege to Linz. The city was never captured, but at one point a fire ignited in Kepler's home and consumed the printing press. It was only through some miracle that the manuscript was saved. This, though, was the final straw for Kepler, who, once the siege was lifted, decided to leave Linz. He travelled to Ulm, where he found a house across the street from the printer Johannes Sauer. Kepler brought his own specially made astronomical type, which he had saved from the burned press. Over the next year, he personally oversaw the publication, carefully proofreading each page. The finished work, published in 1627, was the last great achievement of Kepler's life. It was the culmination of a project that dated not just from the commission of the tables in 1600, but 3 decades earlier, when Tycho began his observations on Venus. Known as the Rudolphine Tables, they marked a decisive break from the past. Earlier astronomical tables were careful revisions of schemes inherited from Ptolemy through the Islamic astronomers until the Alphonsine Tables. By contrast, the Rudolphine Tables, grounded in Tycho's observations and Kepler's new theories, were a genuine revolution, up to 50 times more accurate than what had come before. In an act of modesty, and in tribute to his mentor, Kepler listed Tycho as the first author. Kepler, though, would not live to see the impact of his work. A few years later, he travelled to Regensburg in an attempt to secure a long overdue payment from the imperial court. He fell ill on the journey and was gripped by a high fever. A doctor was called who bled him to no avail, and after several days, drifting in and out of consciousness, on the 15th of November, 1630, Johannes Kepler died. In the years following his death, his theories got little attention. Few people read his work, and even fewer could keep up with his arguments. His 3 laws of planetary astronomy were buried between technical mathematics and mystical speculations. But the success of the Rudolphine Tables made Kepler difficult to ignore. In the practical world of 17th century astronomy, what mattered was where the planets would be at a given time, and in this regard, Kepler's tables were unquestioningly the best. The improvement in accuracy was so great that, for the first time, astronomers could predict not just the general motions of the planets, but the precise moment when fleeting astronomical events would occur. Transits of Mercury and Venus happen a few times in a century, when the planets pass in front of the Sun. It had been known since ancient times that these transits must happen. However, no one had ever observed one. Part of the issue is that when the planets are in transit, their size compared to the Sun is very small, and hence they're difficult to spot. In the case of Mercury, a telescope is needed to see the phenomena at all. By contrast, the transit of Venus can be seen with a good pinhole camera, but the difficulty is predicting with sufficient accuracy when the transit, which only lasts a few hours, will occur. Kepler himself was the first to appreciate that his tables were accurate enough to predict the timing of transits. He calculated that Mercury would pass the face of the Sun on the 5th of May, 1628. Unfortunately, as a telescope is required to view Mercury in transit, and the tables were only published a year previously, this event was missed. In 1631, the year following Kepler's death, another transit of Mercury was due. The French natural philosopher Pierre Gassendi used a modified Galilean telescope to project the image of the Sun onto a canvas. On the 7th of November, Gassendi reported seeing the transit of Mercury, the first person to ever do so. According to Gassendi, while other tables were wrong by several days, Kepler's prediction was only out by a couple of hours. For the remainder of the 17th century, the Rudolphine Tables remained the most accurate source of planetary data. 8 years after Gassendi's observation of Mercury, an Englishman, Jeremiah Horrocks, predicted a transit of Venus based on data from the Rudolphine Tables. The transit had not been forecast by Kepler, who had missed it in his calculations. Using a similar setup to Gassendi, Horrocks viewed the transit of Venus in December 1639. The new level of precision afforded by the Rudolphine Tables was a great boon for Kepler's theories. Whilst the achievements of the new astronomy could be ignored, the predictive power of the Rudolphine Tables could not. His ideas would be re-evaluated and become the bedrock for the new physics which emerged in the latter part of the century. Kepler's work sits between the ancient and the modern. His motivations were spiritual, shaped by a belief that the cosmos reflected a divine order, and his attraction to Copernicanism owed as much to his ideas of harmony as to direct evidence. He convinced himself early that the Sun belonged at the centre of the universe because it symbolized God the Father. Yet, the standards he imposed on his own work were empirical. He accepted ellipses not because they were more elegant, but because circular motion failed to match observation. In this sense, his Christian convictions freed him from the authority of Aristotle and Ptolemy. Kepler's achievements have endured, even as contemporary violence erased much of the world he had inhabited. His final resting place is no longer known. The Protestant cemetery in Regensburg was destroyed during the 30 Years' War, along with Kepler's dream of peace between the faiths. Our only record of his gravestone is a sketch made by a friend. It reads, "I measured the heavens. Now the earth's shadow I measure. My mind was in the heavens. Now the shadow of my body rests."